Okay, great. So what's this one asking us? It's saying we've got a rectangle with sides equal to even integers a and b. It's drawn on the Cartesian plane. Its center, the intersection point of its diagonals, coincides with the point 0, 0. But the sides of the rectangle are not parallel to the axes. Instead, they're forming 45-degree angles with the axes. How many points with integer coordinates are located inside the given rectangle, including on its sides? Okay, so this is kind of interesting. I want to keep this part in mind. Okay, this is kind of an interesting aspect to it. We're going to talk a little bit about that in the not so distant future. But before we do, what else is there to keep in mind here? Well, honestly, if we want to make sense of this, make sense of what it's asking us, I think the best, most effective thing for us to do would be to just take a look downstairs here. Have a look at this picture, because it's worth 1,000 words. This really, I think, clarifies a lot of what we mean over here. This is pretty heavy on the math language. We're talking about integers. We're talking about the intersection point of its diagonals. What do we mean by that? Well, just the center of the rectangle. You know, the way common sense would place the center. What they technically mean is, like, if we were to draw diagonals across the rectangle, they'd intersect right at the middle of it. Anyway, the point is, this is a pretty technical description over here. This is a very nice, easy to understand visual. So that's great. All right, so we understand the problem, right? We're basically saying we've got this big rectangle. Its dimensions are a and b, which are just some whole numbers. We'll take a look at the constraints on those in just a sec. But the idea is that we want to count how many of these points are just falling within the boundaries of this rectangle, and in particular, maybe on its sides. So we'll talk about that. We'll talk about how important that part is in just a minute. But before we do, let's see. So a and b are both positive, even integers. So they're greater than 0. They're both divisible by 2. And they can't be bigger than 50. So, okay, that should be pretty manageable. It's not going to be all that many of these that we'll have to deal with. And it's maybe even less than we might think in terms of the number of cases here, because, I mean, if you think about it, like, it doesn't really matter whether we orient the rectangle the way it is currently, or if we were to orient it more this way. It wouldn't make a difference in terms of the number of dots that are going to be enclosed. I mean, okay, I realize this isn't a very good drawing. Probably I'm missing some of the dots here, but the main thing is it doesn't really matter which way it's been rotated. In other words, it actually doesn't really matter which one's A and which one's B. So we can just, without loss in generality, just make an arbitrary decision about that, and it should work out fine. Okay, cool. So, if anyone has any questions about what this question's actually asking us, let me know. We can talk about those. In terms of how we're actually going to solve it, basically, my plan is the following, okay? Because this is one of those ones, I mean, I know when we're doing one of these problems, we usually like to start with, like, you know, the most naive interpretation, the most brute force, literal interpretation. And we'll sort of try to do that, but the thing is, like, this is not an easy problem. This is kind of a tough one. There isn't exactly like an obvious way to proceed here. I remember the first time I saw this one thinking, wow, now that's a serious problem. So anyway, the point is, what we're going to do here is we'll come up with a bit of a game plan, and then we'll execute that game plan, refine it, etc. So what do we want to do here? Well, first we need to choose a great color. What do you think would go good with these guys? So we've got blue, we've got green, I don't know, maybe some kind of strong fuchsia color. Okay, so my plan for this, I'm noticing this is the labyrinth of nested loops, right? So maybe we'll use some nested loops here, some nested for loops. Kind of makes sense, we're on a plane, so maybe one for the x direction, one for the y direction. So we'll do something like that, sort of brute force. We're gonna section off an area here. So we're gonna basically create this big square, and we'll talk about how we're gonna get this big square over here in just a sec. But before we do, I mean, the main thing that we're doing with this is we're just using this as kind of like an area of possible dots, right? Like all the dots in here will definitely fall within this region It might not cover all of them. It might not encapsulate all the possibilities. Sorry. It will definitely cover all of them. It might be way too big. That's what I'm trying to say. So there's probably going to be a lot in here that's kind of just wasteful. We could probably refine it, tighten it up a bit. But just for our first attempt, I don't think we need to worry too much about the constraints here. I mean, even if it was 50 and 50, I don't think it would, time out. I don't think we could really make it that difficult. So basically our plan is we're just going to section off this area. We know this is a big area, but within this area is definitely all the dots we're looking for. So we just need to make it big enough that, that it's definitely going to cover all these. It doesn't need to be like a tight bound. Or at least not yet. Maybe we'll refine that, like I was saying. But yeah, for now, who cares? Don't worry about it. Okay, cool. So what are we going to do with this? Well, basically, we're just going to run some for loops. We're just going to go all the way through. We're going to check every point. So we'll say, check this point. Is that inside the rectangle? No? Okay, we won't increment the dot counter. What about this one? Is that inside? No? Okay, and we'll basically go through this entire row here, and as soon as we reach the end of this one, so like, we've chosen I guess the y value in this case, and then we move on to a new y value, go through all those x values. So we check all these. We're going to go through like quite a few of these before we find one that's actually going to give us what we're looking for, one that actually would fall within the rectangle. So, I mean, that's fine. Like I said, it means our algorithm is going to be a little bit wasteful, but not to the extent that it would change the time complexity, okay? This would be the first one that actually, gives us what we're looking for. Anyway, the point is, in terms of complexity, I think this algorithm, this brute force kind of thing that's just checking every one of the points, this is going to be quadratic complexity, okay? Order n squared, right? It doesn't really matter in terms of the complexity, it doesn't really matter what the size of this outer square is. It could be huge and it would still be quadratic complexity because it's going to scale up in the same way with the size of the inputs, but it wouldn't necessarily run in the same amount of time as something with a tighter square around it. So, can you have a squared tangent to the rectangle first? Well, yeah. So, like, you mean one that, like, wait a sec, tangent to it. Like you mean one that's just like very, very tightly against it, something like that? Or do you mean like one that's actually like rotated, like the way this one is? I mean, the thing is, like, we'll refine the way the square looks. We're gonna make it a lot better. But for now, we'll just use this outer one. And just to be safe, because we know that in this case, like, what was it? This A was 4, B was 6, or the opposite. So B was 4, A was 6. So 6 is like the biggest side length over here. We know that if we go 6 units out this way, we'll definitely, we'll be covering the area we need to. Right, okay, so basically you're wondering if we could have it sort of touching the 4 corners of the rectangle. Yeah, we could do that, but the thing is, this rectangle won't have integer values for its corners. These will not be integers, and we'll look at that in just a while. I feel like we're spending a lot of time on the whiteboard over here, on the drawing board. Let's actually start writing some code here. Let's dive into this. That'll be fun, right? So basically the idea is that we want to say, let's say const bigness is going to be just math.max of A and B. Yeah, whichever one's bigger. And we're going to use that to sort of decide on the size of the square here. We're also going to say let dots be assigned a value 0. These are the things we're going to be counting and eventually returning at the end of all this. Okay, cool. So what do we want to do within this? Well, basically, like I was saying, we want to run a double for loop. So I think it doesn't really matter if we put the X or the Y first. I think I'm going to start with the Y, so we go row by row, so we go through the entire row, then the next row, and then the next row. So Y should be the outer loop in that case. So Y is going to go from, I guess we'll say from negative bigness to positive bigness. And it's just going to increment up by 1 each time. Okay. And then the inner loop is going to be the X's. That's going to start also at negative bigness. it's going to go until it reaches positive bigness, and then x plus plus. And again, bigness is just sort of this arbitrary variable that we're using to represent like kind of a safe distance. And y equals, like y less than or equal to, as opposed to like strictly less than, well, no reason really aside from the sake of symmetry, because we're saying that it starts at negative bigness. So it's gonna, if it starts at -6, let's say, I'd want it to go all the way to +6, just, you know, so that it's like kind of symmetrical. But good point, like, you know, we could say negative bigness +1 over here, make this one be strictly less than. We'll tighten it up later, but we're not too concerned with it right now. So in here, what do we want to do? Check if the point is in the rectangle. Rectangle. There we go. Okay, cool. So the question is, how are we going to do that? We know that we want to do that. We know that we want to check if the point is in the rectangle, but what does it actually mean for the point to be in the rectangle? What's like a reliable way we could use to actually check that? And by the way, we should probably also mention this. If it's in the rectangle, dots plus plus. You know, we're just gonna add on 1 to this thing. And that's going to be it in terms of what we're going to do with dots, right? It's going to start at 0. We're going to plus plus it every time it's in the rectangle. And yeah, we'll just return that number at the end. So we don't really need to worry too much about it in terms of anything else. It's not like we're going to be performing any other operations, calculations, or formulas on it. So let's talk about this part. This is really the crux of what we're trying to do here. We want to know, what does it mean to check if the point is inside the rectangle? Well, let's think about it in terms of math, right? In terms of geometry, or more accurately, in terms of graphs. Okay, so we, actually wait, that's too similar to one of our other colors. Let's go with, oh yeah, this is a nice color. Okay, cool. So basically, if you think about it, every point that's in this rectangle has the following properties. It is below this line. Okay, and when I say a line, I mean on the mathematical sense, right? This line segment over here lies within a larger infinite line. By the way, in math, anytime we say line, we mean it's perfectly straight, it goes on forever, it has no endpoints. So, you know, if you catch me saying a line to refer to one of these things, what I meant is segment. Anyway, the point is, so this segment lies within this line over here. We know that every one of these points over here is less than this line. They're all going to fall below this line. They're also all going to fall below this line over here. Okay, so is that it? Like, is that the only thing that we need to check? Well, no, not quite, because all these points have another property. Because, like, for example, this point over here, if it falls below both of these lines, but it's not inside the rectangle. So it also has to be above this line over here, and we'll pretend that's straight, and it has to be above this line over here. Okay, so basically the idea is that we have 4 lines. They're going to form the border of our rectangle over here, and yeah, that's what we're going to go with for now. So if we are able to find the equations of these lines, then we should be able to figure this out, because let's say we're looking at dot right here. Yeah, okay, good enough. Okay, so basically we've got this over here. We want to check, is it inside the rectangle? So basically this point over here is going to have both an x value and a y value. So we'll say that's xy over here. Now this line over here would basically have a y equals mx plus b equation, right? So we would say if this, whoa, little jump of the mouse there. Watch it. Okay, y equals mx plus b. And technically we won't really be able to use b because they're already using it up here. So not the same thing, okay? When I say b here, I mean y-intercept. Maybe we should use like a k or something like that. Anyway, the point is, so we've got this line over here, right? So what we'll basically do is we'll take the x value here, we'll put it into the equation of this line to get the corresponding y value, which will be up here. And then we'll compare it to this y value. So we'll say, okay, well the y value we would get from this line is this, like, you know, 1.7 or something like that. Is that is this 1.7 above this y value, -1? Yeah, it is. Okay. So then the only other thing we need to check is if it's also above this y value. So the y value we would get by plugging it into the equation of this line, which would be like a different y equals mx plus b. Any questions on that? So basically the idea is that we need to make sure that when we feed this x value into the equation of this line and this line, we're going to get two y values back, and we need to make sure that this y value falls somewhere between those two y values that we would get. That's going to be our strategy here. Okay? Any questions, comments, or concerns about that? You guys let me know. But for now, we'll continue with this. Maybe I'll just leave this on screen for now. In the tab, so I don't clear it. Yeah. I'll go over here, and I guess we should talk about equations of lines. So normally we have something like this: y equals mx plus b. M and b stand for the slope and the y-intercept. Now it kind of looks like I'm moving the line left and right now, but technically I'm actually moving it up or down. You can tell by the y-intercept. So right now it's 5.3, that's where it's intercepting. If I move it down to, I don't know, like -3 or something like that, then yeah, it moves downward. I know it looks like it's moving right, but you know, that kind of depends. Notice when I change this, the y-intercept is staying still at 3.3. In fact, I don't even need to do that myself. We've got Desmos to do that for us. We can do the same thing with this one. Yeah, tons of fun. Okay, so these are all different examples of lines. Keep in mind, a line with a positive slope goes, you know, up and to the right. A line with a negative slope goes down and to the right. How do we measure slope? Well, rise over run. You might have heard that. So basically, rise over run, what does it mean? Well, let's say we wanted a slope that's going to go up 7 units. For every 3 units, it moves to the right. And it's just going to start at 0 for the sake of simplicity. So check this out. We've got this situation now where basically we'll go 3 units to the right and we'll go 7 units up. And then we get a point that's like directly on the line over here. Okay, so just quick review, y equals mx plus b, equations of lines. Hopefully we're good. So in this case over here, we want to talk about, well, what are the slopes of these lines going to be? Well, these are 45-degree lines, meaning that they go up exactly as far as they go to the right, or down and to the right, depending on the case. So for something like this, the rise and the run would be the same. If it's going to the right 3 units, it's going up 3 units. If it's going left 7 units, it's going down 7 units. So basically, no matter how we slice it, it's going to be a slope of 1. Okay, positive slope, it's going up and to the right. Now this one looks really similar in terms of the rise and run, but notice it's going down, so we would say that this one has a slope of -1. Okay, so just like Rainbow said in the chat, we're either going to have a slope of +1, like this one and this one, or -1, like this one and this one. Okay, so let's, I guess we could take a look at these. So we're going to have something like y equals x plus something. I guess I'll call it b for now. No, I'll call it k for now because we're going to use b for something else. In fact, let's get a and b in here. So a is, for the first one, what, 6? A is 6, b is 4. Okay, cool. So we've got sliders for those. I think they need to be whole numbers that are positive integers, right? So, okay, well, step size of 2 and, step size of 1. No, it should be step size of 2 actually, because they're even integers, right? So, okay, we don't have a whole lot of options. Should we make it go all the way to 50 so we could really look at all the possibilities? Maybe not right now. Let's make it go to 20, I guess, for the time being. That's probably good enough. Yeah, it's not really changing anything for now. But what was it? It was 6 and 4, right? Okay, cool. So we need this k value thing. We need to know, well, what's the actual slope of the line going to be? Let's figure it out. So, okay, basically what we're looking for, this is a bit messy, so I'm going to clear it actually. Basically what we're looking for is this point right here. Actually, not even basically what we're looking for. That's exactly what we're looking for. We're looking for this point right here. It is the y-intercept for our line, which has a slope of 1. And, later we'll find out the other corresponding y-intercept for this one, which is going to be maybe a little bit tougher, but it's fine. Okay, so what do we know about this? Well, I guess maybe we don't know a ton about it, but we could sort of say, like, we've got this right angle triangle over here, right? And the side lengths of this right angle triangle are what we're looking for, right? They are, like, that would be the y-intercept. So if we can find the side length of this right angle triangle, and by the way, it is actually a right isosceles triangle because these two lengths are going to be the same. We know that by virtue of the fact that this is a slope of 1. Okay, so that's nice. The thing is, we want to know, like, for example, what's this? What's the hypotenuse here? That would really help us because we know our, a squared plus b squared equals c squared. We know our Pythagorean theorem. So that would really help us out to find this side length over here. Because if these are the same, then instead of a squared plus b squared equals c squared, it becomes something more like a squared plus a squared equals c squared. Okay, so basically we've got 2a squared equals c squared. Whoa, equals c squared. And we're trying to find the value of c squared. Sorry, we're trying to find the value of c, right? So rearranging, well, all we really need to do is take the square root of both sides. So we'd get root 2a is equal to c. So c is going to be root 2 times a, whatever a is over here, right? Actually, wait, I did this wrong, didn't I? Because we're actually trying to find the value of a. So technically a would be like 1 over root 2 times c. Whoa, okay, cool. Which is the same as root 2 over 2 times c, which if anyone wants a proof of that, we can talk about it. So basically, if we can find whatever c is, then we're just going to multiply it by root 2 over 2, and then that'll give us our a value, the thing we're looking for. Well, what is c? If you think about it, we could actually draw kind of a smaller square that lives within this. Okay, so this is kind of like our small square. We're also going to be looking at the larger square that we could form with this a little later. But check it out. I mean, this is a square, right? We all agree, like this side length over here would be the same as this side length over here. So with that in mind, well, we know this side length because it's the same as this one over here. So this was either b or a, depending on how you're looking at it. So basically, we'll just take our b value or our a value, and that's going to be, what would it be? In this case, it's our b value. Okay, we'll go with that. So we'll take our b value, and that's like our hypotenuse here. So we're going to divide it by root 2. We're going to multiply it by root 2 over 2. So let's get that into Desmos. So we'll say that our k value here, in fact, let's just put it right in here. So we'll say that this is going to be the square root, whoops, don't need that, I guess. Okay, the square root of 2 divided by 2, root 2 over 2. Times what? Times b, I think, right? So root 2 over 2 times b. There we go. Okay. Does that seem about right? It's like 2.7 or something like that. Let's go back over here. Does that seem reasonable, 2.7? Yeah, I would say so. Seems right on. Okay, cool. Now we want to do the same thing, except we sort of want to get this one. Like, what would be the y-intercept of this thing? Well, we can figure that out too, because if you think about it, like this one over here would also form a larger square that the rectangle would live inside of. And this square would have the same side lengths as the longer one, so a. So basically the idea is that this over here, this triangle, same exact reasoning as before. It's an isosceles right triangle. We can use Pythagorean theorem. If we wanted to find the side length over here, it would be root 2 over 2 times whatever this is, and this is a. Okay, so we'll take a, we'll do root 2 over 2, and that's going to give us a new equation of a line. So let's get that in here. Y equals just x. We're just putting x because it's, actually it should be negative x because it's negative 1 for the slope, whereas this is positive 1 for the slope. And then we'll say square root of 2 divided by, whoops, divided by 2. Okay, great, times a. And there we go. So we've got another line over here. It looks like its point of intersection, or sorry, its y-intercept would be like maybe 4.2, 4.3. If we take a look at this one, yeah, that seems probably right. I didn't exactly draw a straight line here. We'd have to kind of extrapolate it, but yeah, 4.2 seems pretty reasonable. I'd say that's within the realm of possibility. Okay, but this isn't really looking like a rectangle so far, so maybe we can refine this a little bit. So what do we need to change here to make it look more like the rectangle we're in search of? Well, we basically have this line over here, and we also have this line over here. Whoa, okay, not even close. Anyway, what we want now is basically the bottom lines, the corresponding ones from the bottom. So this one over here, and this one going this way. Okay, so let's think about it, because these are probably in some ways related to the ones up top. The first thing you might notice is that this one over here, it's parallel to this one down here. And hey, big surprise, but this one over here, it's parallel to this one down here. So they'll have the same slopes. Let's get that in here. So we'll say y equals x for one of them, and y equals negative x for another one of them. And I'm noticing these top two are the same color. Maybe let's make these bottom two also the same color. Yeah. Okay, so it's forming a rectangle now, but not the one we're looking for, because we want the center of the rectangle to be right at the center of the Cartesian plane, 0, 0. So the origin, as we sometimes call it. Because of that, we need to make sure that this distance here is the same as this distance here. So in other words, this one with the slope of 1 is going to have the same y-intercept as this one over here with also the slope of 1, except it's going to be negative. So basically we'll go over here and we'll say, yeah, this one had a slope of 1 and it had a y-intercept of this. Now we're going to take that y-intercept, except we're going to make it negative this time. And now that's looking a bit better, I think. We could do the same thing with this one as well, because just like this, this distance over here needs to be the same as this one over here. So again, same y-intercept as the parallel one, except negative. And I probably should have done this so that, yeah, okay. Is that good? No, that's not good. So that's because this one says B when it should really say A. Great. So that's good. And yeah, rainbow, for sure, it's a parallelogram, but you know, more specifically than that, it's a rectangle, right? A special kind of parallelogram. All right, so cool. This is looking, I think, like what we're looking for in the problem, right? We've got these 4 equations here. We've got 2 of them that are going to define the upper bound and 2 of them that are going to define the lower bound. So what needs to be the case? Well, basically, what we need is for any point that's going to pass all these, it needs to be below this line, but also below this line. So what we could say is we could just take like the Math.min of these 2 red lines and make kind of like a new function out of that. I was about to say a new line, but it's not really. It looks more like this kind of V-shaped thing. So we could do that, you know, we could find an equation for that. We could get that just by doing Math.min of these 2 lines. If we do Math.max of the lower lines, we'll get the same thing, but pointing upward. So maybe we'll start with that and we can kind of refine it from there. Okay, yeah, that'd probably be good, I think, right? Okay, so let's do that. All right, are we ready? Let's try it. So we want to check if the point is in the rectangle. So we'll do something like this. We'll say const upper bound. Or, okay, hold on a sec. Let's make it a function. So let's make it the very first thing we have inside here. Function upper bound. Okay, cool. Of x. Yeah, cool. And all we need to return here is just math.min. Yeah, it was math.min for the upper bound, right? Math.min of what? Well, basically, math.min of this equation and this equation over here. So we'll take in the x, we'll return the math.min of this, so x plus root 2 over 2 times b, and negative x plus root 2 over 2 times a. Yeah. Cool, let's do that. And again, by the way, it doesn't matter which one of these is A and B, but we do have to be consistent with that choice, okay? So if we decide that this one's gonna be B and this one's gonna be A, we can't then flip that around down here, otherwise it won't make sense. It won't give us the right rectangle here. It'll give us something totally different, not what we want. So let's get started with that. So you know what? I'm actually gonna make some constants in here because we're going to be using this a lot. We'll say root 2 is going to be assigned the value of math dot square root of 2. That's going to save us a little bit. So Okay, root 2. So how are we going to use this? Well, it's going to be Math.min of x plus root 2 divided by 2 times b, right? So I'll just do root 2 times b divided by 2, and just a little bit of space in there. And now we'll do comma negative x plus root 2 times a divided by 2. Did I get that right? Yeah, negative x plus root 2 times a over 2. Okay, by the way, if anyone's wondering why I'm saying root 2 times a over 2 instead of root 2 over 2 times a, basically the reason is the following. Oh yeah, let's get a nice brown in there. Okay, so for this, we've got root 2 over 2 times a. Well, a could be written as a fraction. It's just going to be a over 1. Keep in mind the way we multiply fractions is basically just go across. You know, multiply the numerators, multiply the denominators. So what we get from this is root 2 times a, which is root 2a, over 2 times 1, which is 2. So root 2 times a over 2, which is what we have over here. Cool. That's what we're looking for. So that is our upper bound function. Let's get a lower bound function too. Function, lower bound. It'll also take in an x. And keep in mind, this is basically just like the equation of a line, but also with this like Math.min, Math.max. So it's like the equation of two lines being put together. And hey, maybe we'll find a better way to do that later. But for now, we're going to do it like this. So we had one with a slope of x, and I think the y-intercept was negative root 2 times b over 2. And then one with a slope of negative x minus root 2 times a over 2. Did I get that right? Let's verify it. X minus root 2b over 2. Great. And then negative x minus root 2a over 2. Cool. Okay, I think we're good with these. We've got our upper bound. We've got our lower bound. I think we could probably check if the point is in the rectangle. So let's do it. We'll say if upper bound, hold on a sec. If lower bound at x is less than or equal to y, and y is less than or equal to upper bound at x. Under those circumstances, let's do a quick little dots plus plus. And I guess it's pretty clear that if it's in the rectangle dots plus plus, we don't need that comment anymore. So there we go. Okay. Okay, is that gonna work, first of all? Let's try it out. Hey, it works. Okay, cool. So that's nice, that's very satisfying, very nice to see. In case you're wondering, like, why are you comparing the y here to the lower bound of x over here? Well, it's because these are both equations of lines, right? In other words, well, okay, we call these relations in math. It's a special type of equation called a relation. We call it a relation because it relates one variable to another variable. In other words, if we have an x value, we can determine the y value. We can find the y value using this equation, using this relation. So that's what a relation is good for. It's good for basically converting one value into another. It's good for relating to, or it's good for showing how two values are related to each other. So basically this graph over here, all this is a collection of a bunch of points. It's just a whole bunch of dots really closely packed together, densely packed together, like grains of sand on a beach, or even more. But anyway, the point is, all of these dots have one particular property. Every single one of these x and y values represented by the coordinates of these dots will satisfy this equation. In other words, the x value is related to the y value according to this relation right here. Okay, so basically what we're doing is we're saying for any random point in here, let's make it this one, let's say. So we've got an x value and a y value. Well, if we were to feed that x value into this line over here, actually into both of these lines and then find the minimum one, which would be this, and then feed that x value into both of these lines and find the maximum one, which would be this. So we're comparing it to these two, and what are we trying to find? Well, we're trying to find if this point lies within these two. Because let's say we had something with the same x value, but the y value was way up here. Well, this one should not be within the rectangle. It isn't, as we can see, whereas this one is. It's simply because this one has a value that falls between this and this, whereas this one does not fall between this and this. You know, it's not within the habitable zone over here. Now, there's something I want to say about this. The question asked, the question specifically mentioned, including on its sides. So that's what made us do the less than or equal to instead of the strictly less than. So it worked with the less than or equal to. So I guess that means probably they're going to have some edge case in here where it wouldn't work because we're not counting the edge. Wow, that's a really good use of the term edge case. Anyway, let's try submitting this one because obviously it's going to fail. What is it? Oh, well, that's weird. So maybe it's just poor test coverage or something like that. Well, not really. It's that it's not even possible. We can't do it that way. And the reason is because if you think about it, remember how we found all these y-intercepts here were going to be like root 2 over 2 times a or b? Well, a and b are even numbers, right? So that means it's going to basically nullify the 2 here. The 2 is going to get divided out. So it's going to be root 2 times something. Well, root 2 is famously an irrational number. Okay, I mentioned this last time, but there's a group of guys called the Pythagoreans. They believed everything could be expressed as a ratio. One of their members showed them this proof that actually root 2 can't be expressed as a ratio, so I guess it's an irrational number, which is like a new thing. It's exciting, right? And they didn't take too kindly to that, and the guy was mysteriously lost at sea shortly thereafter. So, you know, he was a martyr for the cause. He discovered the irrational number, and look at how far we've come with these. So basically, in this case, since this is an irrational number, it will never, no matter what integer you multiply it by, it will never give you a whole number. It will never give you an integer value. And since the slope is 1, it's going up by 1 each time. That means, so if this is, you know, like 1.718, or sorry, 2.718 or something like that, then this will be 3.718, 4.718. They're going to be irrational in the same way that the first one was irrational. So from the y-intercept, because there's a slope of 1 or -1, we know that if the y-intercept is an irrational number, then every one after that will also be an irrational number. Very, very important, okay? So that means it actually would be impossible for there to be one of these integer coordinate points that falls on the side of this rectangle. So that doesn't actually really change anything aside from maybe saving a couple characters by not having the equal to in here. Maybe it also means we could refine our boundaries a little bit. Who knows? The point is, that's kind of neat, right? Anyway, okay, so how are we doing here? Is this all good? I guess, yeah, this passed all the tests. I'm sort of thinking now, maybe we could kind of refine the way we're doing this. So I'm going to switch these, okay? So instead of y, I'm going to make this one x. I'll make this one the y's. And we'll do something a little different with these. So basically, all right, right now it's quadratic complexity, but it could probably get a little faster, you know, because we're kind of wasting time. Like we're going through 13 of these by 13 of these. If it was like, if one of these was as big as 50, which they can be, right? You know, that could be as big as 50. So let's say one of them was as big as 50. Like, let's say it was 2 by 50. That's probably the biggest ratio of time waste to actual result that we could possibly get. So it's 2 by 50. So we'll say Bigness, where is it? Here, Bigness is going to be 50. It's Math.max, right? So we'd go from -50 to +50. So that's what, like 101 numbers? 101 times 101. What are we up to? Like 10,000 something? It could be a lot, right? So we probably want to stay away from that. So maybe there's a way we could refine this. So we've got our x values. Instead of y going from negative bigness to positive bigness, why don't we do something like this? Let's make it go from lower bound at x to upper bound at x. Yeah, and in fact, instead of lower bound, because remember, if we started at lower bound, it's not going to be a whole number. So maybe we should make it like a math.ceil of this. So it's like the next number up. So math.ceil of the lower bound. So it'll say like, oh, well, the lower bound is going to be like, I don't know, let's choose an x value. We'll say it's -1. Okay, so the lower bound is going to be like this down here, like -3.2 or something like that. Well, we want to round that up to -3, the one that's actually going to work there. Okay, cool. So let's try that. Is that going to work? Yeah, it's going to work. But what else could we say about this? Well, if you think about it, like this is kind of guaranteed, right? Like we're starting this at the lower bound of x, and it's only going up to the upper bound. So do we even need to really check this? Because isn't that sort of taken care of by this? Could we just do dots plus plus? Would that work? And yeah, it sort of looks like it does. So let's actually get rid of this. Let's submit all of this. And yeah, that works. That works. Okay, well, this is getting a little better then. I mean, I kind of like this a bit better. This is starting to get pretty good. There's not too much stuff on the screen. Maybe let's just rearrange a bit, get all of our constants up at the top, declare all of our declarations at the top, something like that. It's not too bad, you know. We've got one little nested loop here. We could probably change this as well if we wanted to tighten up the bound. So basically, we would just need to take the bigger value and find the take the bigger value and divide it by √2/2. Is that, or sorry, multiply it by √2/2? So yeah, let's try that. √2 times the bigger one divided by 2. And let's just do like I guess a math.ceil of that, round it up kind of thing, right? Yeah, I think that's probably good because that'll be sort of like the tightest integer bound we could get, I'm pretty sure. Correct me if I'm wrong. Yeah, so that's good. Like I was saying though, in all this work that we've done since getting our original algorithm working, we haven't actually changed the time complexity, okay? Oh, Rainbow's asking, why does the outer loop need no bounds? This one over here? Like, okay, why do we not need to change the bigness? Like, why didn't we actually have to refine the boundaries on this one in order for it to work? Like, even though we're doing dots plus plus, we're being a little reckless about this. Like you're wondering, why is it that it would work even if we did it like this, right? Like set this to 1,000. Is this still gonna work? And well, obviously it's gonna take a longer time, but yeah, it's still gonna get the values. So yeah, why is that? Well, it has to do with the way that for loops work. Okay, so the way a for loop is gonna work, keep this in mind. This part of the for loop, so the first third of it, right? This is just our declaration. This is something that will run only once as we're setting up the for loop, right? So basically it says y is gonna get assigned this value. This is something that it's going to check every time it executes the loop, okay? And it checks it before it executes the loop. So it's going to say, oh, is it less than the upper bound of x? Oh, it isn't? Oh, well, don't even execute this once then, okay? So basically, that's what's going on. When we're getting into these like -1,000 situations, we're saying, well, actually, in that case, if we're, you know, on this side of it, the lower bound is actually above the upper bound. So there's no possible way. If we're starting with this value here, it couldn't be less than this value here. So it's not even going to make it to the first iteration of the loop. Okay, so we don't need to really check this. We don't need to change these. We don't need to refine the boundaries on the outer loop because it's going to know that there are no points in there. Basically, it's going through, it's looking at the x values and it's saying, okay, how many points are there that are bigger than this and less than this? How many y values are above this and below this? Well, none for any of these. Still out here, above this, below this, not happening. Above this, below this, yeah, now we've got one of them. Okay, so it's only once we actually make it within the rectangle that it's going to start counting those. So does that answer your question, my man? Hopefully. By the way, thank you for asking that because that is a good question. That's yeah, I guess I didn't really explain that part before, so yeah, thanks for that. Okay, so we've got bigness, and again, even though it worked before, notice like this is faster, right? This is working a lot faster than it was before. That might be a coincidence, but the main thing is like the execution time is going to get better even though the time complexity is not getting better. It's still quadratic, right? We still have these nested loops here. The execution time will still scale up with the size of the inputs in the same way, or at least proportionally. But that doesn't mean that's not getting faster. It's getting a lot faster, okay? So this is more of a micro optimization. It's not changing the time complexity, but it is changing the runtime quite significantly. Okay, cool. Let's submit that. We like it. Everyone's very happy. Okay, there are a couple changes I want to make. The first change I want to make is this. So let's, wrong kind of control A. Let's reset the code after we've cut that guy out. We'll paste him in down here. We'll put a big old 1 on the end of it so that if we run this, we'll get a bunch of nulls. Great. So now we're focusing our attention on this guy up here. In fact, you know what? We're going to do this pretty similar to the way we had it before. Let's grab this. We'll paste it in over here. And the only main difference, the only thing that's going to really different from the way we were doing it before is I want to modify these things, our upper bound and lower bound function. So I'm going to change these and then we'll submit that. And then after that, we're going to do a third attempt that's going to be quite different. Okay, so let's go over here for now. Let's clear all this stuff. So basically the idea is that we want to have something like this, right? We want to say, well, this is basically our upper bound. It's kind of this V-shaped function that has its point, it's like a vertex, so to speak, at let's say XY over here. So if we could find the XY coordinate here, that'd actually be super useful because this is maybe actually a familiar looking function. It's an absolute value function. So if we had like Y equals the absolute value of X, that's what it looks like. In fact, let's make that a different color. Let's make it black and visible. Okay, so there we go. We've got this over here. Hey, you know what? Let's switch this to projector mode. That'd be fun, right? Yeah, nice. Okay, cool. So we've got this absolute value function here. It looks nicer, you know, it doesn't have like the big X here. It actually stops as like a V. So if we wanted to make it look more like the upper bound here, we'd have to reflect it in the X-axis. So we'd put a negative outside the function. We'd have to translate it up and to the right. How much though? Like, you know, it looks like the coordinates over here are what, like 3.5, I guess. So we would add 3.5 at the end of it. And it looks like maybe 1.7. It's been moved to the right. So we'll say minus 1.7. I meant 0.7. Sorry about that. Okay, so it's probably going to look a little bit like this. It's a bit off, but the main thing is this is a lot nicer because we don't have to say, okay, here's a line, here's a different line, find Math.min of that line, and then here's a line, here's a different line, and find Math.max of that one. All we have to do is come up with these modified, transformed, absolute value functions. So that's the goal. And really, if you think about it, like aside from the negative out front here, the only modifications we made are translations. In other words, we've just moved it up and to the right. Specifically, we've moved it up a number of units equal to the Y value of this vertex point here. And we've moved it to the right a number of units equal to the X value of this vertex over here, of this point of intersection, really. Because if you think about it, it is a point of intersection. It's a point of intersection between these two lines over here. So how do we find points of intersection? Great question. I'm so glad you asked. There are two ways to do it. Let's look at both of them, I guess. So Y equals, let's try to remember that. Oh, whoops. It's working now, right? Hopefully. Anyway, okay, so let's go over here. We'll say Y equals X plus root 2 over 2 A, was it? Or B? Root 2 over 2 B. Okay, and we're going to say that this is equation 1. And then we're also going to say we've got equation 2, and it's going to be Y equals negative X plus root 2 over 2A, I think. Let's see. Yeah, okay, that looks good. So here's the philosophy. Here's like the thinking behind this, all right? We've got our two equations here. Their point of intersection is going to be, well, okay, let me even back up a little bit further. So let's look at the graph here. Remember, I was saying before that when we're talking about a graph is really just a representation of a relation. What I mean by that is it's just a bunch of dots. Okay, so like this one, well, you know, close to these. All of these are dots that have coordinates that satisfy this equation. In other words, if we were to take the x value and y value of each of these things and put them in for the x and y in this relation, it would make the left side equal to the right side. It would make the equation true. It would make the equal sign telling the truth. Okay, so basically every point on this line is something that satisfies this equation. In fact, okay, we're going to get a bit philosophical for a minute here. You know, it's going to be a little bit of a there is no spoon moment. Shouts out to the Matrix. The point is, there is no line here. Technically, there isn't a line here. It looks like a line, but that's just because we've got infinitely many densely packed together points that satisfy this relation, and when they come together that densely like that, they kind of look like a line. In fact, there's no way to avoid it, but really this is just a whole bunch of points really densely packed together. So that's basically what a graph is. You know, sometimes the points come together to make something that looks like a line. Sometimes the points come together to make things that look like a parabola. Maybe they come together to make things that look like an absolute value function, like a v, and that's what we're after. So we want to get this point, right? The point of intersection here. Well, let's think about it. So that's a point that lies not just on this line over here, but it also lies on this line over here. Now keep in mind, what does it mean to lie on this line? Well, it means it satisfies this equation, okay? So there are infinitely many points that will satisfy that equation. There are infinitely many points that will satisfy this equation, but there's only one point that will satisfy them both. Okay, that's the point we're trying to find. So what we're going to do in order to find that point is we're going to assume that this x over here is equal to this x over here, and this y over here is equal to this y over here. Okay, because keep in mind, these x's and y's can mean totally different things, right? Like this could be an x and y value that satisfies the first equation, but it won't satisfy this equation. It doesn't lie on the line. Whereas this could be an x and y value that will satisfy this equation, but not the other one. This right here is the only set of x and y coordinates that satisfy both equations simultaneously. And that is the fundamental basis of what we're about to do over here. What we're going to start with is something called the method of substitution, okay? So what we're saying is that this y over here is the same as this y over here, this x over here is the same as this x over here. So since, in particular, in this case, since the two y's are equal, we could say, all right, well, since this y equals this y, and this y is equal to x plus root 2 over 2b, well, why don't we just go ahead and replace this y down here with what it's equal to, which is x plus root 2 over 2b. So we'll say, okay, cool, switch colors just for fun, and then we'll say, x plus root 2 over 2b, which is just another fancy way of saying y in this case for the particular y coordinate that we're looking for. What is it equal to? Well, it's equal to the rest of this, right? Just we're basically taking this over here and we're replacing it with what it's equal to. So the other half of the equation was negative x plus hardly an x. Okay, negative x, that's a little closer, but anyway, plus root 2 over 2a. Okay. Cool. Now we're trying to find both the x value and the y value, but now we've got this down to a point where we only have one variable. All we have is the x, so we can solve for that. We're going to add x to both sides to sort of get rid of this negative x over here, so that's going to give us 2x on the left side, and we're going to subtract root 2 over 2b from both sides, so that what we're going to have is root 2 over 2a minus root 2 over 2b. Okay, cool. So then basically that means our x value is going to be, well, we'd have to divide all this by 2, which would give us root 2 over 4, and we can factor that out from both of these. So we get root 2 over 4 times a minus b, unless I did something wrong, which who knows, I probably did. Anyway, so that's our x value, root 2 over 4, a minus b. Cool. But we're not done because we need the y value also. How are we going to get the y value? Well, hey, think about it. We've got two equations here. What do these equations do? What do these relations do? They give you the y value if you know the x value, or vice versa, right? They tell you how the x and y values are related. So really, if we've got the x value that represents the point of intersection of these two lines, we should be able to plug that point of intersection, or at least the x value of that point of intersection, into either of these two equations which both represent lines that this point lies on, and we should be able to therefore get the y value from either of these because it should be the same y value. it's a point of intersection after all, right? So let's give that a try. So basically, if we take a look at this, we should be able to plug it into either of these equations. I don't know if anyone has a preference, but I guess I'll just go with equation 1, because that way I won't have to turn this into a negative. Okay, so maybe that'd be better. Okay, cool. So I'm going to switch colors. Let's make it yellow. And I guess we'll just do something like this. We'll say x, we're going to plug it in. We want to find the y value now. So we're going to say y is equal to x plus root 2 over 2b. Well, what's x equal to? It's root 2 over 4a minus root 2 over 4b. And you're maybe looking at that and saying, well, wait a minute, 0. Why'd you do that? And I thought, you know, you seem so proud of this idea that you could factor out the root 2 over 4 from both of these. Why are you putting it, why are you distributing it right back into these two things? Well, it's because we've got this root 2 over 2b over here, okay? So basically, root 2 over 2 is the same as 2 root 2 over 4. Maybe I should write all that out. Yeah, root 2 over 4a minus root 2 over 4b plus 2 root 2 over 4b. Okay, and I'm just getting these to a common denominator so that I can easily subtract them. So basically what we're going to be left with is root 2 over 4a, and then we're saying minus root 2 over 4b, but then plus 2 root 2 over 4b. So basically the positives end up winning, and we get plus root 2 over 4b, which is basically just the same as root 2 over 4 times a plus b. Cool. There we go. So that's kind of neat. A bit of symmetry to that. We've got root 2 over 4a minus b, root 2 over 4a plus b. Okay, cool. So that's what we call the method of substitution. Let's see if it worked. So let's get this off screen. Let's try to get a new point in here. And it's going to be square root of 2 over 4 times a plus b. Actually, it was a minus b for the x value, I think, right? And then the y value was the one that was the square root of 2 over 4 times a plus b. Oh, wow, look at that. That is pretty nice to see, very satisfying. Okay, cool. So that's our point of intersection. Now, if we wanted to find this one over here, we're basically just rotating it 180 degrees around the origin, which is basically the exact same thing as just reflecting in the x-axis and reflecting in the y-axis. Any rotation can be represented as two reflections. Okay, so because of that, we could just switch the sign of the x value and switch the sign of the y value, and we should be good. So maybe I'll just copy paste this if I can, put that in there, but then say, okay, well, instead of a minus b, it's going to be b minus a because we're switching the sign. And instead of a plus b, it's going to be, well, you know, probably easier to just put a big old negative in front of that. Okay, cool. So, nice. That's pretty nice. That's nice. Okay, cool. So, is that it? You know, I'm thinking now, there's probably something else we could do, but before we get any further, it seems like we've got the points we're looking for. We're going to deal with those in just a sec, but before we do, I just want to mention this method of substitution here. It's just one of the methods we can use. There's another method we could use. Let's take a look at it. We'll just do this one a little quicker. I'll just do like a billion undos over here, and then we'll take a look at this other method. This one was called the method of substitution. The next one we're going to look at is called the method of elimination. This one was substitution because we're basically substituting x plus root 2 over 2b for what it's equal to, which in this case was y. Okay, so that's method of substitution. Method of elimination, if you think about it, we want to eliminate one of our variables here. So elimination is a really fun one. Check this out. This is severely underrated. If anyone here is looking at this and thinking, I'm good with my method of substitution, man, it's going to work just fine. Don't worry about me. Well, hey, I would caution you to say, you know, if ever you think you might encounter a matrix, if ever you're going to do linear algebra, if ever you're going to do Gauss elimination, anything like that, learn your elimination. It's a good thing to know. Any row reduction of matrices is essentially just a way of formalizing the elimination process. So elimination is a really important one. Basically, what we want to do for elimination is we want to eliminate one of our variables. Well, there are two ways we could do that. I mean, I'm looking at this and I'm thinking, hey, if we just add these two equations, what do you think is going to happen to x's here? Let's find out. So we'll get 2y, because it's y plus y, and then x plus negative x is 0, and then we'll just get root 2 over 2b plus root 2 over 2a. Well, that's not bad. And then from there we can say y is equal to root 2 over 4a plus b, which is what we had before. Okay, cool. So that gives us our y value. And that's the same y values we had before, right? Yeah, okay. So I think that was a little quicker. Yeah, this elimination stuff's pretty good. But let's get rid of all this. Let's pretend it never happened. Because I now want to get the x value. Hey, where'd that thing come from? That's weird. All right, so I now want to get the x value. So how are we going to do that? Well, let's eliminate the y. So basically, we'll subtract. Hey, come on. What's up with these phantom keystrokes? Okay, so, or pen strokes, I should say. Anyway, we're subtracting the equations now. So y minus y, well, that's just going to be 0. X minus negative x, well, that's going to be 2x. And then we'll have plus root 2 over 2b minus root 2 over 2a. And yes, Rainbow, definitely. Elimination is very useful in things like linear systems, systems of equations. Absolutely. Okay, so if we wanted to get this, we could do this in a few different ways. We could try to get everything else on the other side by like subtracting root 2 over 2b, adding root 2 over 2a, but I'm just going to subtract 2x from both sides. So we get negative 2x is going to be equal to all this stuff, which is, I'm going to start writing it like this, negative root 2 over 2a plus root 2 over 2b. Why? Why would I write it like that? Well, because when we divide by negative 2, it's going to turn these into 4s, but it's also going to switch the signs on these. So it's going to be root 2 over 4a minus root 2 over 4b, or in other words, root 2 over 4 times a minus b, which is what we had over here. So I think we're all good. Okay, so that was method of elimination. Pretty nice. Pretty nice. So what I would urge you to do is anytime you're trying to solve a system of equations, take a look at your coefficients, see what kind of situation we're looking at. Maybe from there you'll be able to choose the better method. But you know, keep them both in mind. They're both worth knowing. I know they both do the same thing, but they're both worth knowing. Okay, so let's continue with this. What's next? Well, basically we want to get our equation here, right? Our absolute value equation. So it wasn't 0.7 here, it wasn't 3.5 here, it was these things. So basically this was our x value, let's copy that, that's the thing we want to subtract. This was our y value over here, that's the thing that we want to add. If it'll appear, there we go. Okay, come on, come on. All right, so is that working? Well, I guess let's just hide that point. I might as well hide that point now too. And I'm gonna even hide these guys. And check it out. If we move around our a and b values, it looks like, yeah, it's holding up. Okay, well that's cool. It's pretty great. So okay, nice. Let's get that back to what it was. Okay. So then we just need to do the same sort of thing for our lower bound. In fact, I don't think we need that anymore. Okay, so we'll just do. Actually, you know what? I'm gonna take this. Hold on a sec. I'm going to try to be super efficient about this. Let's call this f at x. Okay, so this is a function, f at x. I'm just going to say reflect this thing in the x-axis and reflect it in the y-axis. Well, how do we reflect it in the x-axis? We would say y equals negative f at x. Okay, that's reflecting it in the x-axis. So we're just flipping it upside down. But I also want to reflect it in the y-axis, f at negative x. Okay, and there we go. It's overlapping these other guys down here. Let's get rid of those. And now we basically just have upper bound and lower bound. And that's it. So we can change our values and it's gonna switch these up. But the main thing is that we can just use basically mainly one equation. I mean, we'll start with this one equation over here for our upper bound. And then I'm just gonna do this for the lower bound. I'm going to modify the upper bound to get the lower bound. So hopefully this is stuff that we can keep in mind as I go to a different screen. It's a bit complicated, so I might need to consult this again. But basically the x value is the one that was, yeah, root 2 over 4 a minus b. Let's try that. So for our upper bound, oh no, I already forget. Let's try it. Math.abs. Okay, so math.abs is how we do absolute value. We know that it's being reflected in the x-axis because it's facing downwards. We also know that we want to translate it by how much? I think it was root 2 divided by 4 times something divided by 4. I think it was a minus b. So we'll see how badly I mess this up, and then we'll go from there. Plus root 2 times a plus b over 4. I think it was something like that. Let's try running that and see if it works. Okay, so that works for the upper bound. And then all we're going to do for the lower bound is we'll do something like this. We'll say negative upper bound of negative x, and hopefully that works. It works. Okay, cool. Oh, see you later, Rainbow. Thanks for stopping by, my man. I'll see you again next time, probably tomorrow. Have a good night. All right, so we're done, right? We're done with this? Yeah, cool, that's good. But we're not actually done because we have one more solution left, and it's gonna be the most exciting one yet. So we're gonna clear all this junk, get rid of it. I confirm that, and then we'll just paste it in down here where no one's gonna bother to look at it. Okay, cool, so great. Let's take a look at this stuff over here. Rectangle rotation. We want to start again from scratch. Actually, not totally from scratch. There's one thing that I want to retain from this, which is going to be our root 2. And I don't even know why I bothered copying that. It was probably easy enough for me to just type back in, but oh well. Anyway, the point is, what we want to do with this, and this is a pretty classic thing. I mean, we tend to do this. We're going to rebel against the institution here that's trying to tell us that this labyrinth is just for nested loops. We're going to try to find a way to do this without nested loops. Why do we want that? Well, remember how I was talking for such a long time about how no matter how we do this, no matter how we optimize it, as long as we have these double for loops, we're still falling into this trap of having a quadratic time complexity here, which is not great. It's not ideal. So maybe we can do better than that. Maybe we can do this in linear complexity. Maybe we can do it in like logarithmic complexity. Maybe we can do it in constant time. I mean, that would be great. But we'll try to find that. We'll try to find out what we can do. We'll find the best. Anyway, the point is, I want to switch our perspective on this thing. Okay, so turn your neck 45 degrees, either direction. Okay. Hopefully you've done it. Yeah, okay, so I'm looking at this with my neck turned 45 degrees. Okay, so this, like, to me, this is like the x-axis now, this is the y-axis. Sorry, I just hit the mic. My bad. Anyway, the point is, let's maybe draw this out, make it easier to visualize. So I'm gonna, no, not erase it. Let's just clear the whole thing. Okay, and I'll zoom back in. Great, so let's do this. So we're gonna say, here's our rectangle. Oh, perfect. We're off to such a great start. Oh boy. All right, so what are we gonna do with this? Well, first of all, our rectangle is gonna have a point right in the center, okay? That's the origin. It's definitely gonna have that, okay? Just like this one has the origin there. All right, it's also gonna have probably like a couple other points in here. This is just going to be a sketch. It's not going to be perfect, in case that's not obvious. Anyway, it's also going to go like up with, about the, well, exactly the same distance here, right? And we'll talk about what that distance is in just a sec. And so it'll have some other dots like, like these ones. Okay, so we basically had 3 rows of 5 dots. That's kind of the idea, right? That's what we saw in the example. Yeah, we sort of have that 3 rows of 5 dots. They're not spaced out in the same way that I drew them, but oh well, hopefully that won't be a major problem. And then notice in between those, we also have these, right? We sort of have these additional dots over here. So let's think about those. So we'll put those in there as well. 1, 2, 3, 4, and these 4 as well. So those are basically the dots we're looking at. Okay, cool. So how can we figure this out? How can we figure out just directly like how many of these dots are there gonna be? Well, here's what I propose. We're gonna do it this way. We're gonna say, we're gonna start with this distance over here and this distance over here, okay? So what are these? Well, let's just say without loss in generality that this is A and this is B. So basically this distance is gonna be B over 2. And this distance over here is gonna be A over 2. Okay, nice. Now, here's another thing we know. We know that this is gonna have a length of 1. And any of the diagonals here will have a length of 1. Okay, so that also means that like that would be a right angle. This is an isosceles right angle triangle with side length of 1. And that means, well, hey, this is a special triangle, right? We've seen it before. We could prove this using Pythagorean theorem, but it means that this thing over here is going to be the square root of 2. A squared plus b squared equals c squared. 1 squared plus 1 squared is 2. So basically c squared is 2, which means c is root 2. Great. So nice proof. We've got that this is root 2, and we know that this right here also is root 2. Okay. So let me clean this up a little bit. I feel like there's a lot of junk in here that's just sort of here to, you know, prove the concept or whatever. So we'll say basically this is root 2, and we know that this also is root 2. Now, it probably bears mentioning that this thing halfway between this and this, that's going to be root 2 over 2. So we'll take a look at that a little later. But for now, I want to address basically what I'll call the odd points, okay? The odd dots. I'm calling them the odd ones because there's going to be an odd number of them. That's basically the reason, I guess. It's the ones that are sort of like related to the center of the rectangle. Okay, so we've got the center over here, then we've got all the other odd dots, and there's going to be an odd number of them, right? If the rectangle was smaller to the point that like this one wasn't part of it, well, keep in mind it's symmetrical, so that would mean this one is also not part of it, which would mean again we're back to an odd number. So there will definitely be an odd number in both the row and the column. Okay, cool. So basically, let's work with this. Let's find out how many there are going to be in the row and then how many there are going to be in the column. So the way I want to do this is to say, well, it's an odd number of dots, right? So odd numbers are always going to be of the form 2n plus 1. How do we know that? Well, because every even number is always just 2n for some whole number n, right? That's what makes them even. They're divisible by 2. So 2n is going to be an even number, which means if we add 1 to it, it's an odd number. Take any even number you want. Maybe it's 122. Add 1 to it, you got 123. It's an odd number, okay? And same thing, right? You got an odd number, add 1 to it, you got an even number now. Okay, cool. So this is an odd number. It's going to be of the form 2n plus 1. So ultimately, I think if we figure out what the n is here, then we should be able to get the odd number. Okay, well, we can probably find that n because if you think about it, like we know this dot is going to be included. No matter what a and b are, we're always going to have the center. So if we kind of disregard the center for a minute, then that's kind of like disregarding the 1. It's getting us a step closer to finding the n, okay? Now the next thing is we're actually going to, from the remaining points, which is like, you know, this one, this one, this one, and this one, we've got 4 points. Let's just take a look at half of them, okay? So let's maybe just look at these 2, which means we're kind of getting rid of the 2. So really, if we just find out how many dots there are right here, if we find a way of finding how many dots there are here, then we're finding the n, okay? Which is the most important part for finding this odd number of dots. Okay, so basically, what do I mean by that? Well, for this here, if we want to know how many dots there are going to be, well, there'd be 1 if we could make it root 2 units to the right. So if this a over 2 is bigger than root 2, there's going to be at least 1 dot. If it's bigger than 2 root 2, there's going to be at least 2 dots. Now it's not bigger than 3 root 2, which means we won't have 3 dots. So really, if we're trying to check how many there are going to be, all we need to do is take this number a over 2 and divide it by root 2, and then take the floor. Okay, because we got to round it down, right? Like I realize over here, if we divide this by root 2, we get 1, 2, 0.7 maybe, right? 2.7, well, we don't want that. All we care about is the 2. The 0.7 means nothing to us because it means the next point's going to be out here somewhere, which is not inside the rectangle, so we're not interested. So we're going to take the floor of a divided by 2 divided by root 2. But keep in mind, dividing by a fraction, and root 2 is the same as root 2 over 1, dividing by a fraction is the same as multiplying by the reciprocal. Just the reciprocal, not the negative reciprocal, in case you're thinking about perpendicular lines or something like that. Okay, cool. So from here, well, let's rationalize the denominator. So we'll say we got a over 2 over here. I'm not doing this to get a common denominator. You do not need a common denominator for multiplying fractions. Common misconception. I'm doing this to rationalize the denominator so that we don't have like weird irrational stuff in the denominator, which again, there's a historical reason for that, but we don't need to get into that right now. A times root 2 is root 2a. 2 times 2. Well, I think we probably know that that's 4. So we've got this, and that was the n thing that we're looking for over here. So it's equal to the floor of root 2a divided by 4. That is how many of these things we're going to have. Okay, so that's the number of dots we're going to have in each odd row. Okay, in other words, it's going to be the number of odd columns. Okay, something like that. So we could start with that. We could say const odd columns is going to be assigned the value of 2 times, I'm just going to put an n in here for now, plus 1, okay, for the reason we're looking at. But what did we find that n was? It was math.floor of something like root 2 times a divided by 4 or something like that. Let's see. Root 2 times a divided by 4, take the floor of that, multiply by 2, add 1. Root 2 times a divided by 4, take the floor of it, multiply by 2, add 1. We're good. Okay, so that's the odd columns. Now it would be nice to know how many odd rows there are, because then we can simply multiply those together and we would get all 15 of these odd dots, and that would just leave us with the evens, which we'll take a look at in just a sec. But for now, let's think about it. Well, the same reasoning applies, right? Like we've got an odd number of dots. We're going to disregard the middle one, so we don't have to worry about the plus 1. We're just going to look at this side, so we don't need to worry about the 2. We're just going to take the b divided by 2, divide it by root 2, take the floor of it. So it's going to be the exact same as this, but with a b instead of an a. Okay, well, that works. So we could do something like this, right? Odd rows. And all we need to do is change this to a b. Okay, nice. So we're most of the way there, or we're halfway there, I guess. Times odd rows. But then we're also going to need to add to that the even columns times the even rows, and we don't have those yet. So let's get those in here. Const even columns. Probably don't need that in there. Okay, cool. Even columns is going to be assigned the value of, I don't know, let's just start at 0. And const even rows. Actually, let's make it 2 and 4. So if we do this, then we should get the first one right, because there were 2 even rows and 4 even columns in this case, or vice versa, however you want to think about it. Yeah, cool. We're getting the first one right. That's good. I was hoping that all the other, well, I mean, I was expecting everything else to be wrong because we're just tailoring this to the very first one. Okay, so that basically shows us that this is working, or at least for the first one it's working, which is nice. Okay, so let's continue this. In fact, let's do a whole bunch of undos here. Just kind of delete some of the stuff we added more recently. I just want to get some of the distractions out of our field of view so that we can just focus on the even dots at this point. So when we're talking about even dots, first of all, we're not really going to care about those root 2s, because the thing is, we're not looking at this distance here. What we care about more is this distance over here. So, well, we know that this is going to be halfway between these two. We know that this was root 2, so this is just going to be root 2 over 2. Okay, and then same with this over here. Root 2 over 2 by the exact same reasoning. Half of the square root of 2. Okay, cool. So, how are we going to deal with this one? Well, first of all, we know that it's just going to be like, it's an even number, right? So it's like 2 times n for some n. And in this case, well, we could just say it's however many of the dots are fitting this way. But it's a bit different here because it's not like we're going to have a dot for every root 2 over 2. It's that we'll have a dot after root 2 over 2, but then after that, it's every root 2 beyond that, okay? So from here to the next dot would be a full root 2, and that's why it's over here and not inside the rectangle, okay? So we'll do root 2 over 2, and then from there, it's just root 2, root 2, root 2, etc., just like it was for these other guys. So basically, yeah, it's going to be 2n, but how are we going to find the n? Well, first we're going to add on an extra root 2 over 2 just to make them all the same, you know? So it's kind of like we're extending this to be the same as the rest of them because we don't want any weird outliers, any weird discrepancies. So basically, yeah, we're going to add on root 2 over 2. So we'll take this over here, b over 2. We'll add on root 2 over 2. And then from there, we'll take all that. We'll divide that by root 2 over 1. And whoops, with that, we're going to take the floor of all that. And then we'll multiply that by 2. Okay, that's going to be our goal for this, right? Because half of this is what we get with this. So that's why we're multiplying by 2 at the end. Let me know if you have any questions on how we derived all this stuff. I realize it's a lot of root 2s. It's a lot of pretty sloppy drawings. So, you know, I don't mind clarifying any of this. So, okay, all I want to do now is just clean it up a bit. So the first thing is that we could take what's inside the parentheses, and since they have a common denominator, we could put them together. We could say it's b plus root 2, all of that over 2. And then the other part here is this is the same as multiplying by 1 over root 2, but again, we want to rationalize the denominator, so that's the same as root 2 over 2. Okay, cool. So we got 2 times the floor of, well, let's put this all together, I guess, right? So, okay, b times root 2, that's root 2 times b, or root 2b. Root 2 times root 2, well, by definition, that's 2. That's what square root means. You multiply by itself, you get this number. Okay, and then 2 times 2, well, that's just 4. Great. So that should be it, right? 2 times the floor of root 2b plus 2 over 4. And just, you know, because of the symmetrical nature of this thing, we can say the same thing for these ones over here, that we're basically going to start with a over 2. We're going to add root 2 over 2 to that, divide by root 2, take the floor of that, and multiply by 2. So it's going to be the same thing as this, but with an a there instead of a b. Okay, so root 2 times b plus 2, all divided by 4, take the floor of that, multiply by 2. Let's try to remember all that. Ugh, it's not looking good, but okay. 2 times math.floor of, it was something in here being multiplied by 4, and I think we were adding 2, and we had root 2 times a, I guess, for that one, and then for the other one it'll be b. So let's copy that, let's paste that there, let's put a b on this one, let's try running it, and I think we got it right. Okay, cool. So is that going to pass all the hiddens? Yes, it is. Okay, so that's nice. That's pretty not bad, right? I like it. I think it's good. So maybe there's like just some way we could clean this up a little bit. I'm thinking maybe if we get some functions in here, you know, something like function even dots, something like that, right? With I guess I'll say like D for dimension, dim for dimension. Yeah, okay, something like that. And it's basically just going to return, so it's the even one, right? So it's going to return this thing, but with a dim instead of an A. And I'm kind of looking at this and I'm thinking, you know what? It kind of looks nice to have these all lined up like const. So let's do the same thing for this. So we'll say const even dots is going to be assigned the value of something that takes dimension and maps it onto 2 times math.floor of root 2 times that dimension plus 2 divided by 4. Okay, and then we'll do the same thing for this one over here. So this is going to be like odd dots. Okay, so odd dots, even dots, and odd dots. This is going to be something that takes dim to root 2 times, yeah, that. Okay, cool. And then maybe this will get a little nicer. So let me just delete that. So odd dots. Pardon me. Yeah, I was allergic to that. Anyway, odd dots times b plus even dots of a times even dots of b. Let's try running that. And, ooh, that feels good, I have to say. So, I like this. I think this is a nice solution. I think it looks pretty elegant, to be perfectly honest. So let's try submitting it. Let's see if it passes all the hiddens. And it does. So, what do I like about this so much? Well, I think it looks nice. I think it's well organized. It's a very short looking code. I don't know if it's as clear to the reader as something like this. Maybe, I don't know, it's hard to say. I mean, now that I'm looking at it, these aren't necessarily clear to the reader either, so it's hard to say. But what I really, really like about this one is that it's a constant time algorithm. It's not going to depend on the size of the inputs. So the inputs could be huge, and this one is just going to get done instantly. Okay, it just calculates it right away. It just gives you the exact value you're looking for, and that's it. You know, we don't need to worry about anything else. Don't need to go through any nested loops or anything like that. So while both of these are quadratic time, both of these are, you know, pretty well optimized, but they're still quadratic time. This one over here is going to be our constant time algorithm. So I'd say it's far superior as a result of that. Because even though these didn't get too big, you know, even though A and B didn't get bigger than 50, what if we wanted to modify this? What if we wanted to say, you know, okay, let's put this into a hypothetical situation. Let's say that this was part of some web app that we were trying to do, right? Maybe it's some kind of, I don't know, we're doing some kind of visualizations or something like that, right? And we want to make it so that all the dots in here light up, and like maybe it doesn't even show the rectangle, you just see the dots, and it'd be kind of cool, right? So let's say we want to do something like that, and it's working just fine with one of these algorithms down here, but then one day we want to scale it up. We want to say, oh, you know, we're working on a dot matrix with like 2,500 dots, but now we want to scale it up. Instead of these going up to 50, let's make them go up to 1,000. So now we need 1,000,000 dots. Well, that is going to take a huge hit on the runtime of an algorithm like this or an algorithm like this, whereas it will literally have almost no effect on something like this. Like, it wouldn't even notice that you're saying 1,000,000 instead of 2,500 or whatever, you know. It doesn't matter how big these are, or at least it makes very little difference, you know, like negligible difference, I would say. Anyway, okay, I think this is probably good for now. If you guys want to see more about this time complexity stuff, there is another challenge, another one of these tasks that we completed a while back. I think it was called Apple Boxes. Yeah, I'm pretty sure it was task 30. We did kind of an activity with that one involving time complexity, space complexity. We sort of saw what it means, like what this big O notation is all about. So anyway, if you have any questions, comments, concerns on any of that stuff, definitely feel free to let me know.